Hi everyone, we are going to present about performance analysis of 2T and 3T DRAM with respect to 1T and 1C. These are the contents which we are going to discuss about: introduction to DRAM and problem statement methodologies, 1T, 1C, 2T, 3T DRAM's schematic and read-write operations, and peripherals and array level integration of 1T, 1C, 2T and 3T DRAMs and its read-write operations. Let me give you a brief introduction about DRAM. DRAM stands for Dynamic Random Access Memory. Dynamic means we need to refresh the cells continuously at regular interval of time. Random access means we can access any cells randomly. And it's a volatile memory. Volatile memory means once you power up the data, we will lose the data which is stored in the cell. DRAM is preferred mainly because of its high density, low cost per bit, and low latency. Let us see the place of DRAM in memory hierarchy. It is located in main memory and it's a off-chip memory. The problem statement is the conventional 1T1C DRAM suffers from charge leakages which requires periodic refresh operation which increases the latency and additional power consumption. To overcome this issue, we are going to explore 2T and 3T DRAM which is a capacitorless which reduces the leakages. The methodology we are going to follow is first we are going to design 1T 1C DRAM cell and we will perform read write operation and we will note down the read and write access times. Then we are going to theoretical analysis of 2T and 3T DRAM cells and we will implement 2T and 3T DRAM cells in cadence and verify its operation, read write operations, and we will note down read access time and write access time. And finally, we are going to implement 2T, 3T array level integration and we will verify read write operation with respect to 1T, 1C DRAM cell. The technology node we used is 180 nanometer and we assumed bitline capacitance as 1 picofarad. Supply voltage is 1.8 volt and these are the storage node capacitor values of 1T, 1C, 2T and 3T cells. This is the schematic of 1T 1C DRAM cell. Here we have a sense amplifier and we have a storage node capacitor and we have a access transistor and we have a pre-charge circuitry. Access transistor used to access the capacitor and the sense amplifier is used to sense the change in the bitline voltages and give appropriate voltages again to the bitline, and pre-charge circuitry is used to pre-charge the bitline. Now we are going to see write operation in 1T1C DRAM cell. Initially, we have to pre-charge the bit line to VDD. Once we pre-charge the bit line to VDD, then you have to asset the word line. Once you asset the word line, data will transfer to storage node capacitor by charge transfer. Once charge is transferred to storage node capacitor, you have to de-asset the word line. Now we will see read operation. Initially, we have to pre-charge the bit line to VDD by 2 and then you have to turn on the word line. Once you turn on the word line, charge transfer happen between bitline capacitor to storage node capacitor. Based on the charge stored in storage node capacitor, bitline voltage will going to change either by delta V or minus delta V. If storage node capacitor charges 1 volt, I mean high voltage, then it will change to plus delta V. If it is 0, then it will change to minus delta V. This change in the bitline voltages will be sensed by the sense amplifier and will pull the bitline voltage again to the value stored in the storage node capacitor. Now we will going to look into graphical results of 1T1C write operation. Initially we have to turn on the pre-charge so that the bitline will charge to 1.1 volt. In order to write 1, we have to pre-charge the bitline to 1.1 volt, 1.8 volt, and then you have to asset the word line. Once you turn on the word line, charge transfer will happen between bitline to storage node capacitor. Then storage node capacitor charge will increase from 0 to high voltage. Now we will see write 0 operation. In order to write 0, first we have to discharge the charge stored in the storage node capacitor. So we have to discharge the bitline capacitance by turning on the NMOS, and then it will reach the bitline capacitor voltage to 0 volts, and then you are going to turn on the load line. Once you turn on the load line, if uh, charge stored in the storage node capacitor is high, so that it will discharge to low voltage. Read one operation. In order to read, we need to precharge the bit line to VDD by 2, which is 0.9 volts. Once bit line is precharged to 0.9 volts, you have to asset the load line. Parallelly, we will turn on sense amplifier while read operation. Once you turn on the sense amplifier, since charge stored in the storage node capacitor is 1.8 volt, bitline capacitor will slightly increase. This increase in the bitline voltage will sense by the sensor amplifier and it pulls to 1.8 volt. Similarly, read zero operation. Initially, you have to precharge the bitline to VDD by 2 and then turn on the load line and sense amplifier. The sense amplifier will sense the change in the bitline voltage and rewrite the 0 again into the bitline. The time taken by the sense amplifier to sense and to rewrite the bitline to 0 voltage is 182 nanoseconds. This is the schematic of 2T DRAM cell. These are the two transistors. That's why we will call it as a 2T. Left side part is used for write operation. Right side part is used for read operation. This inverter is used as a sense amplifier to know the charge stored in the parasitic capacitance. This read enable will be enabled to low whenever we are reading the data. Write operation. Bitline is recharged to whatever the data you want to write, and then you will turn on the write word line and data will be charged to this parasitic capacitance from the bitline capacitance, and then we will turn off the word line. In read operation, we will precharge the bitline bar to VDD and then we will pull the read enable from high to low. Once we pull the read enable from high to low, if charge stored in the storage node capacitor, which is a parasitic capacitor, is high, then charge will discharge, bitline charge will discharge to ground. That will sense by the inverter and we will get the corresponding output. Similarly for zero operation also. Let us see the graphical results of 2T write operation. Write 1. Precharge the bit line to 1.8 volts. Then asset the word line. Once you asset the word line, storage node will charge to 1.8 volts. Time taken between once you turn on the word line to charge the storage node to 1.8 volt is 5.6 nanosecond. Similarly, for write 0 also, you have to write the bit line to 0 volts and then you turn on the word line. Once you turn on the word line, high voltage which is stored in the storage node capacitor will discharge to 0 volts. The time taken once you turn on the word line to write 0 is 80 picoseconds. In read operation, in order to read one, initially charge stored in the storage node capacitor is 1.8 volt, and then you have to deasset the read enable to low. Once you pull low, then read operation will start. Since storage node is stored 1.8 volt, that transistor will turn on, and then whatever the charge we whatever the charge in PL bar we precharge it to 1.8 volts, right? That will discharge. This discharge will sense by the inverter and then it will give the output as 1.8 volt. Similarly, for reading the zero, storage node capacitor is 0 volts. We enable the pre-charge and the read. We will pull the read enable to 0 volts. Since charge stored in the at a gate is 0 volts, transistor will not turn on. Bitline voltage you will see as a high voltage only, 1.8 voltage only. The output we will see as a low. There is no delay happen. Schematic of 3T DRAM. These are the three transistors. That's why we will call it as 3T DRAM. Left side part is used for write operation and right side part is used for read operation, and this inverter is used as a sense amplifier, write operation. In order to write whatever the data you want, initially you have to precharge the bit line. Once you precharge the bit line to corresponding value, then you have to turn on the axis transistor of the write, and then charge transfer will happen between bitline capacitor to storage node capacitor, which is a parasitic capacitor. Read operation. Recharge the read bitline to VDD. Turn on the read word line. Once you turn on the read word line, based on the charge stored in storage node capacitor, which is parasitic capacitance, bitline read will discharge or it will hold the charge. Based on this output of sense amplifier, we will get it. As we discussed, for write one operation, recharge the bit line to 1.8 volt, then enable the word line write, and then check the data which is written into the storage node capacitor. The time taken once word line is enabled to write the data is 800 picoseconds. Similarly, for zero operation, bit line is precharged to 0 volts, then turn on the word line, then charge transfer happen between bit line to storage node capacitor. High voltage will pull it to 0 volt and the time taken is 107 picoseconds. Read one operation. Initially precharge the bit line read to 1.8 volts, then turn on the read word line. Once you turn on the read word line, bitline read will discharge. This discharge will sense by the sense amplifier of inverter. It will charge to one output. We will get it as a 1.8 volt, which indicates charge stored in the storage node capacitor is 1.8 volts, and time taken for this operation is 2 nanoseconds. Read 0. Recharge the bitline read to 1.8 volts. Then asset the read word line. Once you asset the read word line, check the sense amplifier output. If sense amplifier output voltage is 0 volts, it indicates it is a 0 volts.
Now we discuss about the peripherals which we are using to make an array, and the peripherals are used to access the array components. So the peripherals which we are used mainly are sense amplifiers and decoders, and the sense amplifier used in the 1 to 1 array is cross coupled inverter with sense margin of 100 millivolts. In 2T and 3T arrays we are going to use the inverter as sense amplifier, and to access the rows, means the word lengths, we use decoders. One of the peripheral component is sense amplifier. Since we have to use it in an array, I have made this into a symbol. Similarly, the peripheral component decoder, to make it use in a array, I have to made the decoder circuit to a symbol. This is the schematic of 1T1C DRAM array. These cells are 1T, means one transistor, one capacitor DRAM cell, which I made it into the symbol. And these are the phase circuitry which is used to precharge the bit lines. And this is the decoder which is used to asset these word lines. And this is the sense amplifier which is used to sense these bit lines. And these are the voltage sources which are present in this slide. Let us see the graphical results of 1T1C DRAM array. Initially, by using the precharge circuitry, we have to precharge the bitline 0, bitline 1, and bitline 2, bitline 3, bitlines 2 VDD by 2, which is 0.9. And the initial values that are stored in the capacitor Q10, Q11, Q12, Q3 are 1001, and by asserting the word line which is done by the decoder, we have to read the bit storage node values 1001, so that we have seen already the bit line, when the storage node is 1, the bit line goes up, the storage node 0, bit line goes 0. Similarly, we have to read the sequence of 1001. Means to read a 0, we have to wait for 186 nanoseconds, and for read 1, we have to wait for 22 nanoseconds. Now I am going to write a sequence of 1, 1, 1, 1 into the DRAM array. Initially, by using the precharge circuit, we have to precharge the bit line to VDD because we are going to write 1 into the array, and then we have to asset the word line by keeping the enable high input at the decoder, and the initial values of the storage node at the storage node is 1001, and when the word line is asserted, this 1001 is getting written into 1111. The time taken for this write operation is 6 nanoseconds. This is the schematic of 3T DRAM array, and this is the 3T DRAM cell which I made it into a symbol. These are the 3T DRAM cells, and these are the pre-charged circuitry, and which is used means different pre-charge circuits are used for pre-charge write bit line and pre-charge read bit line, and these are the decoders. Two decoders are used here because to asset a word line, and another decoder is used to asset the read word line. One decoder is used to asset the write word line, and to access these decoders we have to use another decoder, and these are the sense amplifiers. This is simply an inverter which is used to sense these bit lines. Now I am going to read a sequence 1010 from a 3D DRAM array. To read a cell, to read a value from the cell, we have to asset the read word line first. It is possible through the enable, which is from the decoder, and the initial value stored is 1010, and the stored values are sensed by the initially the sense amplifier outputs are 0000. Sense amplifier input output are 000, and after the asserting of the word line, this one is sensed here, and this zero is sensed here, this one is sensed here, this zero is sensed here. Now I am going to write a sequence of 1 1 1 1 into the DRAM array, so that I want to pre-charge the bit lines to VDD, and then enable the decoder to asset the word line. And when the asserted word line, when the word line is asserted, the initial stored values at the storage node is getting written into 1111 as shown here. This is the schematic of 2T DRAM array, and these are the 2T DRAM cells, which I made it into a symbol. And these are the precharge circuit. These precharge circuits are used to precharge the write bit lines, and these precharge circuit used to precharge the read bit lines. And these decoders are used to asset the word lines, whether it is write word line or it is read word line. And this sense amplifier used to senses the bit senses the voltage difference in these bit lines. Now I am going to read a sequence 1001 from the 2D DRAM array. The initial stored values in the store at the storage nodes are 1001, and the sense amplifier outputs are 0000. And when the read word line is deaccepted, means pulled down to 0, the sense amplifier senses the data which is stored in the storage node and gives the output. Means it senses 1, and it senses 0, and it senses 0, and it senses 1. Therefore the read sequence 1001 is sensed. Now I am going to write a sequence 1111 into the 2D DRAM array, so that we have to first precharge the bit lines to VDD, and then by using the enable signal we have to first on the decoder, and by using the decoder we have to asset the word line, and after the accession of word line, the initial stored value at the storage node 1001 is getting written into 1111. These are the layouts of DRAM cells. This is 1T 1C DRAM cell, layout of 1T 1C DRAM cell. This is 2T DRAM cell. This is a transistor. This is a transistor, and this is the layout of 3T DRAM cell. Here, these are the results we have taken from the graphs and the layouts. This is the read access time of DRAM cells and write access time of DRAM cells, read and write access time of DRAM arrays. Here, the area of DRAM cell 2T, 3T, 1T, 1C. Here, the 1T, 1C area is slightly more than 2T because we are using the capacitor. We are not using the capacitor as a trench or staggered capacitor. Therefore, the area is more than the 2T. But by using the trench capacitance or stack capacitor like structures, we have to decrease this area very much. These are the conclusions we made from this project. Read and write latencies of the DRAM decreases as we going from 1T1C to 2T and 2T to 3T, but there is a trade-off between the latency and the area. If we want to improve the latency, we have to spend the area. Therefore, the cell area and the peripheral circuit area is more. But as we scale down the technology node, parasitic capacitance is also going to reduce. But here, therefore, the storage node capacity also decreases. So in order to increase the storage capacitance, we need to increase the size of the transistor. So the area of the 2T and 3T are like this. And one more conclusion we have drawn here is the DRAM 1T1C is half chip. So there is a one bottleneck between the CPU and the means the logic and the memory. This bottleneck is eliminated by introducing the 2T and 3T DRAMs, because the 3T and 2T DRAMs are entirely fabricated by using the same technology, CMOS technology, but 1T 1C is not processed or means not fabricated by the CMOS technology. These are the conclusions we have drawn, and these are the references we followed. Thank you.